Welcome back. In the next part of this section, we're going to start looking at actually differentiating functions involving natural logs. And we're also going to introduce our friend, the constant e. So far, up till now, we've shown that our definition, the one that's a definite integral definition for natural log, that it follows the common log properties that we've come to know and love. So one thing we haven't mentioned is that E is somehow involved, that there is a base E that's sort of tied into our natural log. And here we're also providing kind of a strange or seemingly strange definition. We're going to define E as the number where natural log of E is equal to 1. So in other words, we're defining E as the place where if you integrate from 1 to E, 1 over t dt, that area would be 1. So the question, of course, on everyone's mind is, number one, why do we do this? And number two, how do we know that this even works? Like, how do I know that there's a number out there where the area must be 1? How do I know that there's only one number that has that property? Like, how do I know that this is a reasonable definition? Because if I want to define a number, I want to make sure that I'm defining it as only one single thing, that there might not be three things that have that property. So the first part, why are we guaranteed there's a number? Well, the answer for that is we know that the range of natural log is all real numbers, so definitely 1 is in the range. And if 1 is in the range, then there needs to be an x value there. So that takes us to 1. So good for us. Definitely there's a guarantee there must be at least one value where natural log has a y value of 1. The question is, how do we know there's only one x value that with that property? And the answer for that is natural log of x is a one-to-one function. So that means if there is a place where it has a y value of 1, then there must be only one place where it has a y value of 1. There won't be multiple places where it has that same y value. So this is a reasonable definition of defining a number because there is only going to be one number. There will be one and only one that would have that property. And then the other nice thing about it is that now that we've defined our natural log of e in this way as being e is the number that makes natural log of e equal to 1, then we also know basically how to solve any natural log equation for any rational number, because if you're thinking about natural log of e to any rational number, using the previous log properties, we know that it would be our rational number times natural log of e, which we now know is 1. So in other words, natural log of e to the n is just n, or in other words, e to the n is the number where it's the number that will solve our natural log of x equals n. In other words, where is natural log of x equals to n? Well, that would be e to the n. So now basically we'll be able to solve log equations if we want to, even though we haven't officially shown that E is 2.71828 or anything else of the sort. I will point out, though, that if you use some of the numerical methods that we used back in section 8.6, so either Simpson's rule or the trapezoid rule, you can show that as you get closer and closer to 2.71828, that the area underneath this curve does indeed get closer and closer to 1. So if you decide to go slicing things up into trapezoids or what have you, you can come up with a pretty good way of convincing yourself that, yeah, indeed, we do have the right E in mind. So this theorem that we have, I've kind of already used it in a sense. The first part is just from what we already said at the very first page of this section, which is because our definition was natural log was a definite integral of 1 over t, integral from 1 to x, that its derivative would be 1 over x. So this, we've basically already proven it or shown it, and that's just coming directly from Fundamental Theorem of Calculus Part 2. And part 2, really, it's just the chain rule, right? There's nothing really fancy here either. Just the one thing that we would have to say in mind here is if we're using the natural log or seeing a natural log in a function and we're differentiating things, we're just going to have to be careful to make note of when is natural log of x, when is it natural log of some function of x, and when is it just natural log of some number. So remember that natural log of something that's a number, of course, that itself is just a constant who would have a derivative of 0. So when I say natural log of u, I'm assuming here that u is a function of x, and specifically one whose derivative exists. The other thing that, of course, we're also assuming here is that u itself is a function who is positive, at least positive for the x values that we're interested in, because if it wasn't positive, then unfortunately natural log of u wouldn't be defined. Other good thing to note, of course, is make sure you're using your log properties. So if I asked you to do the derivative of natural log of x to the 5, you would have to use chain rule. It would be 1 over x to the 5 times the derivative of x to the 5, and then you'd have some cleaning up to do, and you'd eventually get to 5 over x. But if you looked at using that log property of taking the power out front, then you wouldn't have chain rule anymore. Derivative of 5 natural log of x would be 5 times 1 over x. You'd get the same derivative, but a lot faster. And that's going to be a common thing that we're going to see, that as we go through, there's going to be functions that maybe we're going to want to simplify before we differentiate. Okay, so let's start with this first one, and kind of the same thing as just I said for the previous one. I definitely would want to say that this function I could rewrite as 2 natural log of x squared plus 5. So this way I won't have to do a chain rule inside of a chain rule. If I kept it in this form, I would have to do 1 over this expression to the power of 2. Then I would have to deal with the power. Then I would have to deal with the inside. I'd have a function inside of a function inside of a function. This way I still have chain rule to deal with, but it's a lighter and simpler chain rule, because the 2 is now just going to be a constant multiple out front. And for the derivative of natural log of whatever, it's 1 over whatever its natural log of, multiplied by the derivative of what the function was, the derivative of x squared plus 5, which is 2x. So I have 2 times 1 over x squared plus 5 times 2x, which gives me 4x over x squared plus 5. So not too bad. And same sort of thing is going to happen here in G. If I kept the square root as it is, when I look at the derivative of natural log, I'd have, of course, a 1 over the square root, and then I'd have to do derivative of a square root, and that's less than pleasant if we're remembering all those times where we've differentiated functions with square roots. So instead, I'm going to remind myself that square root is the same thing as power of a half, and so I can rewrite this as x cubed times natural log of x plus 1 to the half. And in other words, the half really is just a constant multiple that I'll now be able to take out front. And that's going to make my differentiating a whole lot nicer and easier for me. And so when I look at G prime, I mean, I'm definitely still having a product rule going on. So I have a x cubed and a natural log of x plus 1. So when I do my product rule, I'll just leave that constant multiple out of everybody. I'll have first thing as it is times derivative of the second. Derivative of natural log of x plus 1 is 1 over x plus 1. And derivative of x plus 1 is just 1. So there we go. Plus second function as it is times the derivative of the first, and the derivative of x cubed is 3x squared. So I'll have for my second term 3x squared natural log of x plus 1. And then the last thing that I'll want to do here maybe is just clean things up with the 2. And so what I probably would do here is just to say that I've got x cubed over 2 times x plus 1, and then plus 3 halves x squared natural log of x plus 1. So one thing I want to mention before we leave this example, and this is one thing I just want us to notice, because this is good thing to think about future when we're thinking about integrating. You'll notice we had a function that involved natural logs, and in the process of differentiating, we got a rational function out of it, which means that in the future, sometimes when we're looking at integrating rational functions, that our antiderivative might involve a natural log. So that's a good thing to think about sort of for future purposes. Okay, so here's another one, the pretty standard one of us finding an equation of a tangent line. So here I want the equation of the tangent line to this function at x equals 1. And before I do anything else, I'm going to quickly figure out what the point is, just so that I've got my x and y coordinates all kind of squared away. So when x is 1, the y value should be natural log of 1 plus 1 cubed, so that's 2 cubed, times square root of 1 over 1 squared plus 1, so in other words 2, and whole thing squared. When I clean that up, I get 8 over 4, which is 2, so we've got natural log of 2. So there we go. My point is the point 1 natural log of 2. So this is one of the places where, you'll be sort of happy when you start to see natural logs coming along because of all the properties we have. If you were to differentiate this as it currently is, the inside is a quotient, which has also got a product built in, and also some chain rule built in, which is kind of a nightmare. But the good news is that we can rewrite what y is, and we have all those lovely log properties, which means that instead of having y being one big gigantic logarithm, I could rewrite it as a bunch of simpler logarithms. I could split it up as 3 natural log of x plus 1 plus half natural log of x minus 2 natural log of x squared plus 1. So just basically using the log properties that we saw earlier, we were able to split this into sums and differences of natural logs, and that our powers would be able to come out front, and of course the square root, that's a power as well. So now taking a look at this is way easier to differentiate. I have no quotients to deal with at all, or products. And most of the derivatives are pretty fast to do. Natural log of x plus 1 is 1 over x plus 1 times the derivative of x plus 1, which is just 1. 1 half natural log of x, its derivative is 1 over x. And natural log of x squared plus 1, that would be 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. So our derivative, 3 over x plus 1 plus 1 over 2x minus 4x over x squared plus 1. And so now we can find out what our slope is. And so for that, I'm going to put in my x value of 1. So at 1, the slope would be 3 over 2 plus 1 over 2 minus 4 times 1 over 1 squared plus 1, which is 2, and all this actually adds up to 0. So it turns out we've got a horizontal tangent line. So that's kind of nice. That means maybe we've got a max or a min going on. So if we were thinking about that, maybe that would be something to consider. But here we're just interested in the tangent line. So now my tangent line, I'll create its equation. So we have y minus the y coordinate equals slope times x minus the x coordinate. The y value was natural log of 2, the slope was 0, the x value was 1. So we're just going to get the straight line y equals natural log of 2. And there we go. That would be the equation of our tangent line to the curve that we were given. And that is lovely. Course, all the old things that we saw in the past can come back to haunt us, specifically taking derivatives implicitly. So here we have an implicitly defined function with natural logs and all the rest, and we're looking for dy dx. So I'm going to do kind of same thing that we did as the previous one. I'm going to first simplify my equation. So here I'm going to rewrite this as natural log of x plus natural log of y. And for natural log of x plus 1 squared, I'll take the 2 out front. And so now that I have this a little bit simplified, I can now differentiate with respect to x. So I'll need to remind myself that when I'm differentiating natural log of x, that'll just be 1 over x. But when I differentiate natural log of y, it'll be 1 over y multiplied by the derivative of y. And the derivative of y is dy dx. Okay, next term, 2 times natural log of x plus 1. I'll have 2 times 1 over x plus 1. So I'll get 2 over x plus 1. And on the right side, the derivative of y cubed. So power rule will happen. And then the derivative of y itself is dy dx. And then the last little bits that I'll have to do is just cleaning stuff up. So I'm going to leave everybody with x's on the one side. So there we go. I've got that accomplished. And on the right side, I'll move everybody with dy dx's. Then I'm going to do a couple of things. So the first thing, I'm going to clean up this. I'm just going to make this a little bit nicer. If you made common denominators and added everybody together, you'd multiply this top and bottom by x plus 1, this top and bottom by 2. You would have 3x plus 1 over x times x plus 1 after you cleaned it all up. And on the right side, I can factor out dy dx. And I'd have 3y squared minus 1 over y. And I could do the same sort of thing that I did on the left side, make common denominators and combine everybody together. And so if I were to do that, then that would give me a 3y cubed minus 1 over y. And so now if I wanted to go and solve for dy dx, I just need to divide the left side by this big fraction, and that'll give me a y times a 3x plus 1 in the top, and x plus 1, 3y cubed minus 1 for the bottom. And there we go. We have our derivative of y with respect to x, and we found it implicitly. Okay, one last one to do before a pause. So let's take a look at this function, natural log of x over x. Just as a little side note, I'm going to make a note here that its domain is definitely all the numbers that are larger than 0. Because I'm going to be finding critical points and finding mins and maxes and coordinates of inflection points and all the rest. And so the one thing I wanted to just make a note of is my domain is 0. And so later on, I'm going to notice that my derivatives are not defined at 0, which is not going to be a big surprise. But since 0 is the end point of my domain, I'm not going to include it as a critical number. Because we'd only be including it as a critical number if possibly you'd be making some sort of change happening there. You might be changing from increasing on one side to decreasing on the other, and you might need to know that information. But there's no graph on the left side of 0, so we don't really care what's happening as we're getting close to 0, at least not for max and min purposes. So for us, I'm going to start by finding our derivative, and I have to notice that this is a quotient, so when I find the derivative, I'll need to use quotient rule. Not hard to do, so bottom gets squared, bottom comes up, derivative of the top, derivative of natural log of x is 1 over x, and then minus the top as it is, times the derivative of the bottom, and the derivative of x is just 1. So when we clean things up, we get 1 minus natural log of x over x squared. While I'm handy, and I've got it handy here, I'm going to find the second derivative as well. And so for that, quotient rule would need to happen again. You'd have to square the bottom would come up. Derivative of the top, derivative of 1 would be 0, and derivative of negative natural log of x would be minus 1 over x. And then minus the top as it is, times the derivative of the bottom, and the derivative of x squared is 2x. You could clean things up a little bit here. You'll notice that when I clean things up, I'll have the x and the x canceling, so that I'll have minus x and I'll have a minus 2x times 1 minus natural log of x, and on the bottom I'll have x to the 4. If you did a little bit of cleaning things up, you'd be able to see that at the very end of it all, I would wind up getting 2x natural log of x minus 3x over x to the 4, and then I could cancel out an x from everybody top and bottom to give me 2 natural log of x minus 3 over x cubed. And there we go. We've got our first and our second derivative handy. So first part, if we're thinking about critical numbers, I can do that right here right away, because for our critical numbers, we need to look for where is the derivative equal to 0, or where is it undefined. I already said undefined at 0, but I'm not going to include 0 in my little list of things to care about because that's at the end point of my domain. So instead, I'm only interested in where is my derivative equal to 0, and the derivative being equal to 0 means that 1 minus natural log of x would need to be equal to 0, which means that natural log of x is 1. And we know that that would mean that we would have e to the 1 as our value for x, because that's what we said e was. E was the value such that natural log of e is 1. While we're here, we can also find the y value on our curve for that point. So the y value would be natural log of e over e, which is 1 over e. So we actually have a critical number, e, and the point is e 1 over e. That's our point. So now next thing that we want to do is figure out, is this critical point, is this going to be a max, a min, what's the story? And for that, we have our second derivative test that we're going to be using. And of course, for that, I use the second derivative. So now the next part that I need to do is figure out what's going on with my second derivative when x is equal to e. So my second derivative when x is equal to e, my second derivative was 2 natural log of x minus 3 over x cubed. And now I can evaluate this right away. Natural log of e, I know that that's 1. So in the numerator, I'd have 2 minus 3, which is negative 1 over e cubed. E itself, so you'll notice we still haven't talked about e having the value 2 point whatever it might be. I know that because e is a number such that the integral from 1 to e gives us a definite integral value of 1. Whatever e is, it's on the right side of the x-axis. It's definitely positive, which means whatever e is, e cubed is also positive, which means negative 1 over e cubed is definitely negative. So therefore, we are concave down, and so by the second derivative test, we know that we have a relative max at our point e 1 over e. Okay, so turns out we had an extremum, and it's a relative max, and that's the only one we have. If we're interested in points of inflection, we'd need to think about the second derivative again, and if we were interested in concavity, again, we'd need to think about the second derivative. We know for the second derivative, it's equal to 0 when the numerator is equal to 0. So in other words, when 2 natural log of x minus 3 is equal to 0. And we'd find that that's when natural log of x is 3/2. And we said we already know how to solve this sort of an equation. The number would be e to the 3/2. So x is e to the 3/2. If we wanted to figure out the y value, we could always go back to the original function, and that would be natural log of e to the 3/2 over e to the 3/2, which is 3/2 over e to the 3/2, or 3 over 2e to the 3/2. As far as concavity goes, we've actually already got half of our work cut out for us, because we already figured out for the value of e that the second derivative at e was negative, which meant we were concave down. We already knew that. We did that one earlier. E to the 3/2 is our number that we're interested in, so I'll look at a number to the right of it. So that might be, for example, e squared. And if I look at my second derivative at e squared, I would say that it would be 2 natural log of e squared minus 3. I can figure out that that numerator turns out to be positive 1, and that our denominator would be e squared to the power of 3, which is e to the 6. We'd find our second derivative is positive. That would give us something that's concave up. So in other words, we have a point of inflection. At that point, e to the 3 halves, 3 over 2e to the 3 halves.